There are many chemical reactions that are equilibrium reactions. In this video, we'll look at equilibrium reactions involving acids and bases. A few common acids and bases include sulfuric acid and car batteries, acetic acid and vinegar, and amino acids, which are found in proteins. We're going to look at three equilibrium reactions: the acid dissociation reaction, the base hydrolysis reaction, and the water dissociation reaction. A buffer is a substance that resists change in pH, and we can apply acid-base equilibrium principles to make a buffer of a certain pH. Buffers are used to preserve food. Next time you're eating, take a look at the food label to see if any of these substances are in there. They'll be used as buffers. You may use fruit fresh to keep your fruit from turning brown. Citric acid is the buffer, and then vitamin C is the antioxidant. Here are two other products to keep your fruit fresh. Note that these products contain acid, in this case citric acid, and sodium citrate is the conjugate base of citric acid. Calcium ascorbate is the conjugate base of vitamin C. If you don't like your apples turning brown, now you can buy genetically engineered apples that won't turn brown. And check out this factoid of information. Let's take a look at the acid dissociation reaction. Note that one water behaves like an acid, and it donates its proton to the other water, which behaves like a base. The two products are H3O plus and OH minus. Now, chemists like to take shortcuts just like everyone else, so the shortcut for this reaction is H2O produces H plus, which is the same as H3O plus, and OH minus. Note that this reaction has an equilibrium constant, we call it Kw, of 1 times 10 to the minus 14. So stop the video and answer these two questions. So here are the answers. Water has a pH of 7 because when we do an equilibrium calculation and solve for H plus, we get 1 times 10 to the minus 7. If we convert the H plus concentration to pH using this formula, we get pH equals 7. Now in that equilibrium calculation, H plus equals OH minus, which equals 1 times 10 to the minus 7, so pH 7 is considered neutral because the concentration of H plus equals the concentration of OH minus. Every acid has a partner or conjugate base. For example, HA, when it gives up its proton, forms A minus. So A minus is its conjugate base. A base also has a conjugate acid, so note that water behaves like a base. When it accepts a proton to form H3O plus, that is the conjugate acid of water. So here's a shortcut way of writing that above equation. And let's practice writing conjugate acids and bases. So answer these two questions. So when sulfuric acid loses the proton, it forms HSO4 minus its conjugate base. When the base OH minus accepts a proton, it forms its conjugate acid H2O. There are strong acids and there are weak acids. We can quantify how strong or weak an acid is by looking at the equilibrium constant, which tells us the relative amounts of reactants to products. So let's take a look at the common acid HCl, hydrochloric acid. Which picture best represents HCl? So stop the video and answer that question. Since HCl is a strong acid, A represents HCl. Let's take a look at acetic acid. Stop the video and answer this question. Since acetic acid is a weak acid, the answer is D. And here are the reasons. Let's relate acid strength to H plus concentration and pH. So stop the video and answer this question. So the answer is 1. Remember that higher H plus concentration means lower pH. If you have a strong acid and weak acid of the same concentration, turns out that the weak acid will have a higher pH. For example, why does a 0.1 molar HCl solution have a pH of 1? Here's the answer. To calculate the pH of a 0.1 molar acetic acid solution, which is a weak acid, we have to do an equilibrium calculation. So stop the video and try an equilibrium calculation to figure out the pH of this solution. And here is the answer. The very small acid dissociation constant tells us hardly any of the acetic acid is going to break up into its ions. This shows how to set up your equilibrium calculation. And then we substitute these values, which are the equilibrium concentrations, into our equilibrium constant expression. To simplify our calculation, we can assume this 0.1 minus x is approximately equal to 0.1 since Ka is very small. Solving for x gives us our H plus concentration, and then plugging into our pH formula gives us a pH of 2.9. You just calculated that a 0.1 molar acetic acid solution has a pH 2.9, but vinegar, which is 0.9 molar acetic acid, has a pH of 2.4. So stop the video and answer this question. So here's the answer. Apply Le Chatelier's principle. So by adding more reactant or increase the concentration, that shifts the reaction toward the product side and makes more H+. Higher H+ means lower pH. Do weak acids have the same weakness? So let's compare two weak acids, aspirin and acetic acid. Which acid is stronger and why? Compare the Ka of each acid. Turns out that the stronger acid has the larger Ka, and that will be aspirin. Here's the structure of aspirin, and the acidic proton is this one. So let's practice an equilibrium calculation. Stop the video and calculate the pH of a 0.1 molar aspirin solution. Set up an equilibrium calculation like you did 2 slides ago. Use this value of Ka, and you'll turn up with a pH of 2.3. Not only can acids be strong or weak, so can bases. So stop the video and identify which statement is true. I'm pretty sure you identified that statement 2 is the true statement. Let's add the acid dissociation and base hydrolysis equations together. Stop the video and see what you get. So here's what you get. Note that HA and A minus are on each side of the equation, and we're left with the water dissociation reaction. And here's an equation to remember. Kw equals Ka times Kb. We calculated the pH of a weak acid earlier. Now let's calculate the pH of a weak base. The acetate ion is the conjugate base of acetic acid. So stop the video and follow these steps to calculate the pH of a 0.1 molar acetate solution. And here is the answer. Note that Kb, the base hydrolysis equilibrium constant, is calculated from Ka using this equation. Then we do another equilibrium calculation. Make that simplifying assumption to make our calculation easier. X is the hydroxide ion concentration. From OH minus we can calculate POH, and then we can calculate pH from this formula. Note that for a base, the pH should be greater than 7. Let's practice calculating the pH of a weak base. Sodium benzoate is used as a food preservative. What is the pH of a 0.1 molar sodium benzoate solution? Stop the video and follow the same steps as we did earlier. Here is the base hydrolysis reaction. Kb is calculated from this formula. Then set up an equilibrium calculation and solve for X. Then calculate the POH and finally the pH. Practice makes perfect, so do another equilibrium calculation and calculate the pH of a 0.1 molar baking soda solution. Note that pKa gives you Ka. Then you calculate Kb. Then do your equilibrium calculation to calculate X, which is equal to OH minus, which is 5.0 times 10 minus 5. Then you calculate pOH, and finally pH. We mentioned sulfuric acid at the beginning of the video. It's used in car batteries, so stop the video and answer this question. Here's the answer. H2SO4 is a strong acid. It dissociates completely into H plus and HSO4 minus, but HSO4 minus is a weak acid, and it partially, or actually hardly any HSO4 minus associates into H plus and SO4 2 minus. So the major sulfur-containing substance in sulfuric acid is going to be HSO4 minus.